Welcome to part 4 of this video playlist about the best methods for alkylating amines. This video is about the use of alkenes as alkylating reagents. Both electron-rich and electron-deficient alkenes can alkylate amines, but the reaction conditions may vary a lot. Electron-deficient terminal alkenes readily add amines, without the need of strong bases or other catalysts. Less electron-deficient alkenes, however, do not usually react with amines unless the amine has been deprotonated by a strong base. The regioselectivity of these additions is such that the most stable carbanion is formed as intermediate. Ethylene, for instance, reacts at 100 degrees Celsius with secondary aliphatic amines in the presence of catalytic amounts of sodium, as shown here. Higher olefins, however, do react more slowly than ethylene, and if more acidic amines are to be ethylated, for instance aniline, then a much higher reaction temperature is required. Thus, the reaction of aniline with propene in the presence of 8% of sodium only yielded 43% of N-isopropyl-aniline at 300 degrees Celsius. Interestingly, if instead of sodium aluminum is used as methylating catalyst, no N-alkylation but only an alkylation of the phenyl group occurs. Styrenes react more readily with strong nucleophiles than simple terminal alkenes, and aniline, for instance, cleanly adds to styrene upon heating in the presence of catalytic amounts of sodium. It has been recently discovered that such reactions proceed under much milder conditions if conducted in the presence of air, probably by intermediate formation of radicals. It remains to be seen if this can also be realized in a controlled fashion on a larger scale. In this example, 5% of a strontium amide was used as catalyst, again to promote the addition of piperidine to styrene. A good yield of the expected phenethylamine was obtained after only 5 hours at 60 degrees Celsius. According to an older article in Chemische Berichte, the sodium salt of allyl alcohol can mediate the addition of piperidine to allyl alcohol. Interestingly, butyllithium does not add to deprotonated allyl alcohol at the terminal methylene group, but at C2. In this more recent example, piperidine was alkylated at nitrogen by treatment with terminal alkenes and catalytic amounts of a ruthenium complex under an atmosphere of carbon monoxide and hydrogen. This reaction was a sequential hydroformylation of the alkene followed by a reductive alkylation of the amine by the intermediate aldehyde. Thus, one additional carbon atom, originating from carbon monoxide, was introduced between the nitrogen atom and the terminal methylene group. This is one of those rare examples where an amine could be alkylated at nitrogen under acidic conditions. Treatment of toluidine with an excess of isobutylene and pyridinium hydrobromide at 140 degrees Celsius for 5 days gave a substantial yield of N-terz-butyltoluidine. As a side reaction, though, some arene alkylation occurred too. As mentioned above, aliphatic primary or secondary amines readily add to electron-deficient alkenes, such as ethyl crotonate, as in this example. Such additions are, however, sensitive to steric effects. Alpha-beta unsaturated esters with 2 substituents at C3 are much less reactive than crotonates, which in turn are much less reactive than acrylates. Thus, 3,3-dimethyl-acrylate did not react with piperidine under those conditions where crotonate reacted cleanly. If instead of piperidine the sterically less demanding methylamine was used as nucleophile, however, then the addition proceeded again as expected. Cinnamates are also quite unreactive electrophiles. Treatment of ethyl cinnamate with an excess of diethylamine at 200 degrees Celsius, for instance, did not yield any alkylated amine, but only some diethylamide and unchanged starting ester, no matter if the reaction was conducted in a solvent or neat. Even with methylamine at 100 degrees Celsius, no complete addition to the cinnamate double bond occurred, and mixtures of esters and amides were obtained. These experiments also show that ethyl esters cannot be readily converted into amides just by treatment with an amine. Usually, some catalysts will be required to attain a complete conversion, but it is often easier to use a more reactive carboxylic acid derivative, such as a chloride or a more reactive ester. So, what are the potential side reactions? If the nucleophile is an aniline, the most common byproducts are C-alkylated anilines. The examples on this and the previous slides show that it cannot be predicted with certainty if a given alkene will react with an aniline at nitrogen or at carbon. Some alkenes also oligomerize readily, in particular at high concentration or in the presence of radicals or strong acids or bases. Thus, many of these reactions will usually require some optimization. Here are some further, mostly recent examples to help you get a feel for the possibilities of this chemistry. The next video is about alternative strategies for the alkylation of amines. These include less direct methods based on protecting and activating groups, for instance the alkylation of sulfonamides. See you there.